Okay, Brittany, please share this link to me on Slack.
Thank you. I'm gonna get coffee too.
Oh, send it to Crystal. Where did Crystal go?
She's right there. I'll go tell her because I'm gonna get some coffee.
She does. You send it. Oh yes, I see it.
Okay.
Yeah, it's got this.
All right.
I figured out what I needed, so you're fine. Okay, Suna, I am sending you a link in the chat box, which is the YouTube stream. So if for whatever reason Skype isn't working very well, you can switch over to that. How is this? Well, the sound right now with me talking, you can probably hear fine. We'll test it with Kevin in a minute. The room is a bit loud, so it might be hard until he starts.
Yeah, so far it's working well.
Okay. You can see the screen okay?
Yes.
And then he'll be standing to the, oh, it's the other direction. Can you see Kevin where he is now?
I can't see Kevin.
Kevin, wave your arm so I can tell where you are.
Oh, thanks.
Okay, yeah, I know, it's hard. He's like this big on me. All right. So hang tight while we get everything. Kevin, say something loud.
So it'll be tough for
Quiet, everybody. For 1 second.
We're just gonna test the sound.
oh, audio test. Test.
Suna, can you hear okay?
Yes, that's great.
Thank
No
you.
problem.
Thanks, everyone.
Right, stay quiet. All right, so good afternoon and welcome. Thank you for coming to this Astrophysical Sciences and Technology Ph.D. Dissertation defense. Our candidate today is Cooke, and in a moment I will ask his advisor, Dr. Jason Tardelby, to say a few words about him. But before that, just some procedural things. This is the public part of the defense. Kevin will spend the next 40 minutes or so telling us about the work that he's done over the last few years. After that, there will be time for questions. Please, if you do have questions, hold them to the end so that Kevin can keep to time. Following that, there will be a closed committee session, so the rest of the audience will leave at that point. So with that, let me introduce Dr. James Tardelby.
All right. Hi, everyone. So it's a great pleasure for me to introduce Kevin Cooke before his PhD dissertation defense. It's especially special for me because Kevin is my first PhD student. I first met Kevin during my first year here as a faculty member while he was a third-year PhD student. And we first met because he came by my office looking for a research supervisor. And so we talked about various research projects. We wound up finding a project that managed to combine what he had been working on previously, which he will tell you about, and my own work with large surveys at high redshift. And so I think we found a pretty good niche to combine those two different interests into a fairly unique PhD topic. A lot of what you'll hear about were Kevin's own ideas, and he has led the project and its various directions very well with very little interference for me, except when we did. So along the way, I mean, you'll hear a lot about what he has done in terms of his research projects, but along the way, he has done a lot of other things that you won't hear about. He has learned how to process Hubble data, which he probably won't tell you too many details about. He has gone on an observing run with me to Keck, learned how to observe, learned how to process the resulting spectroscopy. He learned how to process near-spec spectroscopy, which was actually quite complicated. And in addition to research, he's been active in a number of other ways here at RIT, as many of you know, in terms of being interested in public outreach, in terms of his interest in NASA missions and the history of spaceflight, which he has told us all about at numerous astro lunches, and we've all learned a lot more about the history of spaceflight as a result of that. And he has become very interested in public policy. As you all know, he has been selected as the College of Science graduate student delegate. So at the graduation ceremonies in a few weeks, we'll get to hear him again tell us something. We will see, whatever his speech is about. And so with that, I will conclude and let Kevin tell you all about what he has been doing for the past several years.
Thank you very much, Jehan, for the introduction, and thank you all for coming here today to listen to the research that I've done as part of my dissertation, titled Magnificent Constructions, the Role of Environment and the Stellar Mass Growth of Massive Galaxies. And I wanted to say thanks to the many collaborators that worked on me through these 4 projects that you'll be hearing about today. And I wanted to especially thank the Galaxy Evolution Research Group here at RIT for providing such a magnificent environment in which to do this work. And we've all done research on galaxy evolution in our own different ways. And my own angle on this is to analyze how the most massive galaxies in the universe grow their stellar mass, how they become the most massive. These exceptional objects are called brightest cluster galaxies. So here is an image I've used many, many times because it shows how the great diversity in galaxies out in the universe. The most massive galaxies, brightest cluster galaxies, or as I will refer to them, BCGs throughout the talk, are seen in the bottom left of this image. And what you see is something that really looks like a smooth smudge. It doesn't look very much like the galaxies that you may be familiar with that are very much like the Milky Way, such as in the top right, which have spiral arms, which have newer colors, and which have obscuring dust lanes. That's because BCGs are composed of basically one old stellar population, which explains the yellow to reddish color. Additionally, they have very, very sparse gas and dust supplies to form new stars, and so you don't see very much obscuration in that galaxy in the bottom left. You also don't see any new structures. There are no new stars forming. Now, while this is normal for BCGs throughout the modern universe, there are some exceptions. Here is the brightest cluster galaxy, the Phoenix cluster, and instead of a smooth distribution of stars, you see these filamentary structures surrounding the BCG, and those structures are coming from cooling gas throughout the galaxy cluster, condensing and basically falling into the gravitational potential well of the brightest cluster galaxy, which is very often close to the gravitational potential well of the cluster in total itself. Additionally, there are some also extremely rare objects that called BCGs that are forming stars. Here is an example observed by RIT alum Grant Tremblay, in which you see 2 brightest cluster galaxies, or 2 massive ellipticals, coalescing, and during that coalescence, the sparse gas supplies within each of them are being compressed against each other, and that compression is triggering new star formation. And so you can see in this right zoom in, this filamentary structure with nodes of many stars forming at a given time. And you can see that they also emit in blue light, which makes them really, really easy to detect in comparison to the old stellar populations surrounding them. So we expect that brightest cluster galaxies are the smooth, old galaxies that you see in this image here, but there are some exceptions. And these exceptions that have been observed served as the instigating idea for my dissertation which had the objectives of determining what are the growth phases for these massive galaxies, and how does this compare with the overall galaxy population at that time in the universe. And so to address these objectives, my dissertation took the form of 4 projects that looked at BCGs and their progenitors further and further out in the universe. The first project was a follow-up towards that emerging brightest cluster galaxy system that I showed you an image of just earlier, in which we wanted to investigate the star formation rates of BCGs in the most massive clusters, since the merging cluster that I showed you was in one of these highly massive samples. And so what we did was we selected BCGs from the Sloan Giant Arc Survey and the Cluster Lensing and Supernova Survey Hubble, nicknamed CLASH, and we would estimate star formation rates using a variety of methods. Some monochromatic methods would just look at a single analysis, such as using the emission from H-alpha or O2, or using the ultraviolet emission observed with GALAX. Now, these methods would only look at star formation that is not obscured by the birth clouds that are condensing to form stars. So that only gives us a partial measurement. To find a total measurement of star formation, both that we can immediately see or any star formation that is buried within the gas clouds forming these stars, we fit the observations from the deep to the near infrared of these galaxies, and I'll be talking to you all a lot more about what that process entails once I get to Project 3. Now, with these estimations of how many stars are being formed in these BCGs, thanks to our spectral energy distribution fits, we can make a plot like this. Here on the y-axis, I have specific star formation rate. So this is in units of solar masses per year, the amount of stars being formed, divided by the total stellar mass, the amount of stars that are already there. So it gives you a good indication as to what fraction of the galaxy is forming right now. And the numbers for the BCGs that we observed are extremely low. These measurements are made in units of inverse years, basically giving you a quick estimate of the mass doubling time for how quickly the galaxy can double in stellar mass. It's a useful tool for identifying how long it took for the galaxy to get all that mass in the first place. And with specific star formation rates below 10 to the negative 12, that's less than a Hubble time. So with their mass doubling speeds being so slow that it would take longer than the age of the universe to form them, that means that they needed some sort of highly star-forming past in order to form those stars. We also identified that there was systematic offsets between our sample, which is in the red and blue, in comparison to other samples that were selected just using the infrared, which was the Hoffer sample as the green plus symbols, and just optical emission lines like H-alpha and O2, like I used, which is the Lewidol 2012, which is the purple triangles. We also push out this investigation of brightest cluster galaxies out to higher redshifts, out to about a redshift of 0.6 or 0.7, which is about 8 billion years after the Big Bang. Now, this effectively follows the standard model of brightest cluster galaxies. They're all very quiescent. They're not forming very many stars anymore. But we did find one other notable exception. This galaxy, SDSS J1336, is another merging BCG system. The two nuclei of the two separate galaxies are not as clearly distinct as the one that I showed you earlier. And part of the reason for that is that you can see obscuring dust lanes in between the two nuclei. And it's within those dust lanes, within this green circle here, that we measure a star formation rate of about 3 to 4 solar masses per year. And so we expect there to be even more star formation throughout the entire complex. So overall for this first project, we found that star formation still is very, very rare, even though we've started seeing these exceptional merging systems triggering star formation. And any sort of stellar mass growth requires something that isn't delivering gas to form stars, which is something called a gas pour or a dry merger, in which a second smaller galaxy without very much of a gas supply drops into the BCG, just adding old stars, and that's it. Finally, in this project, we looked at the observed radio power of our sample, and the radioluminosities tended to be nearly an order of magnitude greater than would be expected, thanks to purely star formation. Radio can be naturally emitted from the star formation process, and as stars die, but the emission that we see is not nearly enough. The emission that we see is so much that the emission, thanks to star formation, is not nearly enough. This first project served as the stepping stone towards my second work, which I did in collaboration with Dr. Kevin Fogarty, in which we wanted to investigate how stellar populations of brightest cluster galaxies age with time. And so what we did was, instead of combining two separate cluster samples like I did in Project 1, we looked at just the most massive galaxies in well-detected groups and clusters in the Cosmos survey, which I'll talk to you all about a bit soon. What we did was we limited our sample to between redshift 0 and 1, which should constrain our sample to purely as BCGs are shutting down their star formation. So this is after the cosmic peak of forming stars. We limited our sample to greater than 30 high probability members, so we would know that we are looking at well understood groups and clusters. This gave us a total of 42 high mass groups and clusters, and to identify the brightest cluster galaxy within each of these, we used Dr. Fogarty's custom spectral energy distribution tools to fit every confirmed galaxy of every group to estimate all of their stellar masses, and then selected only the most massive out of each group, and treated that as our brightest cluster galaxy. For cases where the BCG was within a factor of 2 of the second most massive galaxy, we consider that second most massive galaxy as well as a secondary sample called massive group galaxies. Normally in the present day universe, BCGs are more than twice the mass of the second most massive galaxy. It's one of the many things that make them unique. So for groups where you don't see that clear distinction, we wanted to make sure that we were including everything. To plot how the stellar populations are aging, here I have a plot of mass to light ratio in the near infrared at 3.4 microns as a function of redshift on the x-axis. Now, mass to light ratio is an interesting quantity. The higher the number that means that you need more stellar mass to emit whatever unit of luminosity that you're seeing, which is telling you that the stellar population is very inefficient at radiating because you need a lot of mass in stars to accomplish it. And so as this number increases, that's telling you that your stellar population is dominated by lots of low mass old stars. If you have a very low mass to light ratio, that means that your emission is being dominated by very efficient, very massive stars. And those massive stars can only exist for the few million years after a star formation episode. And what we see is that for both brightest cluster galaxies in the dark blue and large member galaxies, which were within a factor of 2 in stellar mass, we see the same trend. In fact, it's a very tightly confined trend in which the stellar populations are passively aging with time, without very much variation. We do find one outlier to this trend here in the bottom right. That's because this is one exceptional object that includes a supermassive black hole that is actively accreting matter and emitting across the entire EM spectrum. And that's messing up our mass to light ratio calculations, because for this specific plot, we were just fitting for purely stellar emission and dust obscuration. Now, this trend is very useful because it's so tightly confined, you can fit a linear relation to it, and that gives you a conversion between the 3.4 micron luminosity that you observe with your telescope, the distance the galaxy is away from you, redshift, which you should know, and that can give you a stellar mass estimates to use in your work. And so this is something that we've made available to the field. Finally, the other very important result of Project 2 was the detection of a possible dependence with the total mass of the cluster in which these galaxies are living. On the y-axis, I have specific star formation rate again. So for this, the higher the value is, the greater the fraction of itself is currently forming stars. So higher means more star formation, usually. And on the x-axis is the total mass of the total dynamical mass of the galaxy cluster in which the BCG is living. And for our sample, which is the dark blue and the teal again, we occupy this intermediate group and cluster mass parameter space, and we find that there's a pretty low level of dispersion of specific star formation rate values being a bit over an order of magnitude. But when we compare this to other works that look at BCGs for more massive clusters with total dynamical masses above 10 to the 14 solar masses, we see a much wider dispersion and a much higher ceiling for the specific star formation rates hosted by their BCGs. This can be taken as evidence that more massive galaxy clusters either have a longer-lived fuel source that can contribute to the star formation rate in these galaxies, or the BCGs within these systems are also hosting a higher degree of gas to form stars. And since we were looking at galaxies from redshift 0 to 1, which is a very wide span of time, about 7 billion years, the fact that you see them also tightly confined in specific star formation rate in comparison to all these other surveys is telling you that some sort of environmental dependence. The BCG is acting in such a way in relation to its local environment by redshift 1. And so for my next project, the goal was to better understand how that environmental dependence came to be. So what about high redshift? If you start going towards the earliest eras of the universe, what do we see in terms of massive galaxies and star formation to begin with, not thinking about BCGs in particular? Well, it's been observed that there's already a population of quenched early type galaxies, quenched being that star formation has already started to shut down, and they're early type, meaning that they're elliptical, the oval shape that I showed you at the beginning of the talk. So the formation mechanism for these massive galaxies needs to be able to shut down star formation earlier than redshift 1, or at least start that process. Additionally, these high redshift candidates have an effective radius. Their physical size can be half to a quarter the radius of the galaxies that we see in the present day universe. So very quickly, they actually puff up with time into the giants that we see today. And even with all of this advanced evolution happening early in the history of the universe, we still see some unique systems that are forming stars. So this is telling us that in order to observe their progenitors at early times, we need to be very careful about how we select them. We want to use something that is independent of color or star formation rate, because that's all very sensitive on what's going on. We don't want to limit our sample to purely those that are forming stars early in the universe or those that have already shut down. So to find these progenitors, we use data from the Cosmos survey, which I'll talk about on the next slide. Because Cosmos is sensitive enough to detect galaxies about 10 to the 10 solar masses out to a redshift 3. To give you some relation as to what that means, the peak of cosmic star formation rate density in the history of the universe was at around redshift 2. So by going out to redshift 3, we cover both the peak of star formation in the universe and the eras immediately before and after it. Additionally, the galaxies that we observed near present day are above 10 to the 11.5 solar masses, so more than order of magnitude greater. And so being sensitive in order of magnitude and more in lower stellar mass gives us a lot of parameter space to find progenitors. But that doesn't answer the question of how we actually identify them. That's because there are a lot of galaxies out there. The Cosmos survey is an area 2 square degrees on the sky, about 9 times the area of the full moon. There are some comparison galaxy surveys here, such as the Hubble Ultra Deep Field, for scale and comparison. And in Cosmos, there are well over 2 million galaxies detected. And Cosmos has been observed all across the EM spectrum, from the X-ray to the radio. But today we'll just be using the ultraviolet to the far infrared to constrain star formation rates and stellar masses. So out of all these galaxies and out of all this data, how do we identify which ones are the special ones, the progenitors of the most massive galaxies in the universe? I use a method called the evolving co-moving cumulative number density method. It's kind of complicated, so I'm going to start you off with a simple diagram. Let's imagine that we have a box of all of the galaxies in the universe within a known volume. This cartoon is a graphic representation of the galaxy stellar mass function, meaning that you have very many low mass galaxies, an intermediate number of intermediate mass galaxies, and very rare, very massive galaxies. As you run the clock forward, all of these galaxies across the stellar mass are going to be forming stars using their gas supplies. And so once you get closer to present day, all these galaxies within your box of the universe have increased in stellar mass. They've also changed in star formation rate. They've changed in the color that you see them as star formation rate shuts down. And this is what makes it very difficult to identify progenitors, because they'll look very different than their descendants. However, the trick is in acknowledging that galaxies inhabit the universe at a given density. So if you have a population that you're investigating near present day, they inhabit a volume element of the universe at a given density. It's expected that their progenitors will inhabit a volume element of the universe at the same density. And so that gives you a way to identify the progenitors of a galaxy population that you're looking at, as long as it's defined by stellar mass. Now, you may immediately be saying, Kevin, this isn't quite true. Sure, you have all of these galaxies in the box, but they're not static. They're not just sitting there. Galaxies merge. You just showed us pictures of this earlier. And so that's right. That is a problem with a constant co-moving number density method, where you assume that the density is constant. But you can add in corrections for how many of the lower mass galaxies in the early universe merge onto your brightest cluster galaxy seeds. You can add in a correction for how many of these low mass galaxies to include. To get that correction, we turn our sights to the simulated universes that have been produced by theorists, specifically the Illustris project, which is a cosmological simulation that includes not only dark matter physics, but also baryonic physics, and includes star formation within the simulation itself. And what that simulation and their published results give us is a correction. Here on this plot is number density for a given galaxy population defined by mass, either 10 to 11.5 solar masses, 10 to 11 solar masses, 10 to 10 solar masses, and so on. They inhabit Illustris at a given density at present day. And when you turn the clock backwards in time, looking towards the early universe, the most massive progenitors and also the galaxies that are being merged onto those seeds are counted together. And as you include more and more merger partners, that increases the number of galaxies you're looking at, increasing the density of your sample, because you're stuffing more galaxies into that volume element. And so what we use is this dashed line here for the most massive galaxies, telling us how the density of the progenitors is increasing as you look further back in time. So this is very abstract because it's in terms of number densities. That's very tough to equate to the physical objects that you see out in the night sky. So I'm going to do one last explanation for how this works because it's so important. Here is a plot that is not that complicated, even though it looks like it's a lot of lines. On the y-axis is the number of galaxies you have per bin in stellar mass being on the x-axis. All of these lines show the same thing, the number of galaxies at a given mass. Each color corresponds to a different time in the universe, with the highest lines starting at gray being close to modern day. And then as you look at the lines that are decreasing, you're looking further back in the history of the universe. That's because as you look further back in the history of the universe, you don't have as many high mass things. So, in the present day universe, we have a certain sample of galaxies that at the most massive end that we want to investigate. That corresponds to a given number density when you integrate this curve. You count out all the galaxies within your volume. Thanks to the Illustris simulation predictions, we know what number to integrate down to using the other mass functions at different times in the universe. So if you go out to redshift 2, that tells you you need to integrate down to a certain value. That gives you a new stellar mass cut that's lower, which makes sense because the progenitors should be less massive than the ones in modern day. And you can do this further and further out in terms of redshift. So we have a sample that's defined by stellar mass. We know which galaxies we're looking for, but what about their local environment? That's the whole goal of this project, to find out how that environmental dependence came to be. We use the cosmos density fields produced by Ben and Darvish et al. And here's an example of the cosmos field in terms of density, measured in terms of multiple of the average mean density across this slice of the cosmos field. What you do is you take slices of the field that you're looking at, going further and further out in terms of distance, corresponding to earlier and earlier in the history of the universe. And we identify 3 different environments: dense environments, which are greater than twice the mean density, which is the green and red regions here on this map. There's an intergroup environment, which is suspended in between these groups and clusters, which is in dark blue, which is defined as between the mean density and twice the mean density. And finally, there's the fields, the very sparse regions of the universe where galaxies inhabit below the mean density at that redshift, which is identified in white here, and will be identified as a blue in the upcoming plots. So we know what galaxies to look for. We know what their local environments are thanks to these maps. How do we estimate their star formation rates? Here is the explanation of a spectral energy distribution fitting that I talked about at the beginning of the talk. On the y-axis, I have luminosity of the galaxy, and on the x-axis is wavelength. And there is the far ultraviolet here on the far left, going through the optical, near-infrared, mid-infrared, and then far infrared on the very far right. The red points are observed values of a real galaxy out in the Cosmos survey. And first, I use a program called MagPhys to fit 2 components to these galaxies. First, a stellar population, so just stars. And then this model also takes into consideration the obscuration of gas and dust obscuring that starlight. So here on this plot, you see this gray dashed line. That is if the galaxy is purely stars and those stars are emitting. But that's not realistic. A galaxy is more than just stars. This black line is the final fit, which includes stars and the gas obscuring their light. This energy that is absorbed by the gas, that's being blocked by the gas, heats up the gas and dust, and then the dust re-emits out in the far infrared. And this far infrared is especially important because that's where you can get a total star formation rate estimate of stars forming both in areas that you can observe through their birth clouds and areas that are obscure, because the far infrared emission can pass through that gas supply. Now, this doesn't always work, because as I said, that a galaxy is not just stars. A galaxy is not just stars and gas and dust. It can include a feeding supermassive black hole. And so sometimes you'll get a fit that is way off. You can see that the solid black line in this MagPhys fit does not match those red points at all. And it's estimating a star formation around 256 solar masses per year, which is really, really high. The Milky Way has about 1 to 2 solar masses per year. We use a secondary program called SED3FIT, which includes a stellar component, which is in blue, the dust component, which is in red, and what is special is the green component, which is an actively accreting supermassive black hole called an active galactic nucleus, or an AGN. And you can see that with this third component, the mid-infrared is fit significantly better, and the star formation rate goes significantly down, 45 solar masses per year instead of 240 solar masses per year. Fortunately, corrections like this are very, very rare in our sample, and it only occurs about 1%. And what we do is we use the MagPhys fits when the final fit matches very well with the mid-infrared points that you see there, defined to be about half the fractional luminosity. So if the fit is off by a factor of about 0.4, then we know that it's doing a bad job. And then we use the SE3 fits instead. And this is where we get our star formation rate estimates. So we have our star formation rate estimates, and we have our environmental estimates. What do we see? Here on this plot is the key results of Project 3. On the y-axis, we have stellar mass growth rate. It is in units like star formation rate, solar masses per year being added, but there is an additional correction that has been applied to it to correct for the most massive stars dying off very quickly. They're not permanently adding to your total mass. And what we see is that the green line is going to be the total stellar mass growth. That's the important line that you should take into consideration. So that's how fast these galaxies are growing with time. And you can see that it's going down as you get closer to present day. The blue and red lines are the stellar mass growth rates just due to the star formation estimates that we have corrected for stellar mass loss in galaxies that are in field environments in blue and dense environments. So what will become galaxy clusters in the modern day universe. And we see that the star formation rate growth behavior changes in 3 phases. First, at high redshift, very early in the history of the universe, the total growth that we see due to star formation is consistent with the total growth of stellar mass of our sample. The blue and red lines are consistent with the total growth line. Then there is this intermediate era in which star formation is good for about half of the total growth rate, but then you need something else supplying this stellar mass being added to your galaxies. And this difference between the lines is a growth deficit that can be made up by galaxy mergers, galaxies combining with the progenitor and supplying additional stellar mass in addition to the star formation that is occurring. Finally, as we get closer to present day and closer to redshift 1, where the other studies were, we see that the growth due to star formation drops off precipitously, especially in dense environments, whereas the progenitors in field environments can maintain their star formation for a little bit longer, but then unfortunately we lose sample size. And the reason this region is hatched like this is that there is only one galaxy that's satisfied her stellar mass cut and is in a field environment at a redshift of 0.5, which makes sense. That's a good sanity check that we're looking at a population that is transitioning to become these very massive galaxies hosted exclusively in clusters. Additionally, there was another line on this plot that I didn't talk about yet, the gray dashed line. That is purely stellar mass being delivered thanks to galaxy mergers as measured by the illustrious cosmological simulation. Now, you'll notice that it is higher than the total growth rate that we do observe. That's okay. This line is presuming that during a galaxy merger, all of the stellar mass is being added onto your progenitor. And it's been observed in the low redshift universe that galaxy mergers are not that efficient. Some of the stars are going to be unbound and flung out into the intracluster medium surrounding the galaxies. So this dashed line can decrease by up to a factor of 2, depending on what papers you look at. And that would be consistent with the total growth rate that we see, and everything will add up to the green line. So we now understand that there are these 3 eras of star formation or merger-dominated growth. What do the galaxies look like in terms of color? How are they transitioning from a blue star-forming population to a red quiescent one? Here I have the same plot done in 6 different redshift bins, starting from our highest redshift bin early in the universe to low redshift in the top left. And on the y-axis, I have a near UV minus R band color, and on the x-axis, I have R minus J band color. And this parameter space can be separated into 2 different spaces: a quiescent space in which galaxies are classically red and dead, and a star-forming space in which galaxies are blue and forming stars. And what we observe is that our progenitor sample smoothly transitions from this star-forming color space to a quiescent space at around redshift 1, which is consistent with this transformation in star formation growth that we see here on this earlier plot. I also added a color bar to these points for galaxies where we had measured surface brightness profiles. This is measured in terms of a Sursec index. What this means is that the higher the value, the more concentrated your light is, and so that's very much like an elliptical galaxy. The lower the value of Sursec index, the more spread out the light is, which is very consistent with disk-like galaxies. We don't really see too much of an evolution with time. I have the median Sursec index for any of the bins that had more than one Sursec index measured. And we see that they are consistent within the errors of each other across all of these redshifts, and they are slightly above or below 2.5. So towards high redshift, they are pretty similar to S0s, where you have a large bulge component with a disk, possibly as well, if you were to believe the estimates thanks to Sursec index, which then may transition towards a more peaked surface brightness profile on lower redshifts. But they're still pretty consistent within errors of each other. Sursec index really gives you a global value as to how the light is distributed in these galaxies. So what do they actually look like if you were to load up a picture? Now, while there's over 1,400 progenitors, so I can't show you them all, 3 of us in the project did go through the about 1,300 or so that had HST imaging in the field of cosmos and labeled them either an elliptical, or called spheroid, or a disk galaxy, or a composite in which you had both of those components. And so on this next plot, I'm going to show you the total number of each of those classifications over redshift for our sample. So I have redshift on the x-axis and the total number of a given classification on the y-axis. A galaxy is counted as a spheroid, unclassifiable, irregular, or disk-like galaxy if 2 out of the 3 of the classifiers agreed on that classification. So spheroids are very much like the elliptical galaxies that you've seen before. Disks, very much like the Milky Way. Irregulars are a mess, where you can't tell what it is. And there's a rising fraction of unclassifiable galaxies as you get to higher redshifts, as the bulk of the stellar emission is redshifted into infrared bands that we have less coverage of in the cosmos field. So unfortunately, we're only able to identify the morphologies for a fraction of the sample very early in the history of the universe. But we do see a sample that is dominated by either unclassifiables and spheroids or purely spheroids, which is pretty consistent with the S0 type that I showed you in the previous plot. And next, what we can do is count everyone's labels together as to whether it included a disk component or a spheroidal bulge component. And that is a diskiness value that I have plotted here on this plot on the y-axis. The higher number of disk labels were given to the galaxies within a given redshift bin. And environment bin, so field, intergroup, and dense again, is plotted here. Basically what we did is we assigned each label a numerical value, disk being +1, spheroid being -1, and we averaged all of the classifiers' classifications together, and then averaged the average of each galaxy for all the galaxies within a given sample. Now what you see for this top plot is there isn't too much of an evolution with environment. At high redshift, you only see it start to manifest below redshift 1. This could possibly be real or possibly due to the rising fraction of unclassifiable galaxies at high redshift, making it difficult to really pin down what's going on. But we do recover the density morphology relation at low redshift, in which dense environments host predominantly spheroidal galaxies and field environments host predominantly disky galaxies. Now, just as I separated my sample into a star-forming and quiescent sample using their NUV, R, and J colors earlier, I did the same for this sample, and what we see is something interesting in which the quiescent galaxies that have stopped forming stars transition from this composite bulge and disk morphology to a spheroidal type very quickly. This process starts very early in the history of the universe, while the star-forming galaxies remain this composite disk plus bulge morphology. So overall, what we found in Project 3 was that BCG progenitors grow through 3 important phases of growth: star formation dominated at high redshift, then this intermediate era in which you need star formation and gas-rich and gas-poor mergers from redshifts about 2.2 to 1.2, and then below redshift 1.2, you need gas-poor mergers to just directly add stellar mass to them. And we do not see any dependence with environment until you get to low redshift. So at high redshift, we really don't see very much. And this is kind of the frontier of the field because measuring local environment at high redshift is pretty difficult. We don't detect any evolution in Tersec index, but we do see a clear transition from star-forming blue color to a quiescent red color with time. And we also see that the quiescent galaxies are transitioning into the spheroidal ellipticals that we see today. As you may ask, how does this compare with the general population? And that is the setup for my 4th and final project, in which we sought to understand the star formation stellar mass main sequence. So here's a cartoon of what that represents. The number of stars that a galaxy is currently forming is found to be often correlated with the stellar mass, the number of stars that already exist there. And the vast majority of galaxies belong to this small parameter space that has been nicknamed the main sequence. Now, don't be fooled, galaxies don't travel this relation like a railroad track, as in going straight up. Galaxies individually may shut down their star formation very early, thanks to whatever unique history they may have. And once they are shut down, they belong in this low star formation rate parameter space where all the red and dead galaxies are. A galaxy may jump up momentarily and have very high star formation rates, and that's called a starbursting galaxy. And there's also an intermediate population called the Green Valley, which is believed to be galaxies that are slowly transitioning off the main sequence before they finally kind of give up on star formation and become red and dead. So what do we know about this relation? Well, we know that the shape of it has been observed pretty well out to a redshift of 2.5. And towards the more massive end, there can be a flattening in which this cartoon is a bit of a simple version. You actually see this sequence drop off. After a certain amount of stellar mass, your star formation rate isn't scaling with it. There has been some environmental effects observed at low redshift, below redshift 1, but there's only been a few very recent works trying to investigate whether this trend changes based on where a galaxy is living at high redshift. And so for Project 4, we wanted to identify at what redshifts and stellar masses and environmental dependence comes into play. Our sample is the total Cosmos 2015 sample above their stellar mass completeness limit. What you're seeing is about 118,000 galaxies plotted in 20 equally separated contour levels. And so as you go out in redshift, you are being limited towards observing the brightest and most massive galaxies. But we're going to use all the galaxies above this dashed line, since we are detecting over 90% of all the galaxies above that stellar mass. So just like we fit the spectral energy distributions of the galaxies before, we do that again for this sample to find their star formation rates. And what do we see? We see, so in each of these plots, I have star formation rate in log units. So in log units on the y-axis, and in stellar mass on the x-axis. At low redshift, you can see the line of the main sequence pretty clearly. The solid line is the median of the star formation rate of just the star-forming subsample that we observed. And I've also plotted 2 comparison lines from the literature. And what we see is that as you go out to higher and higher redshifts, the normalization of the population increases. Everything is forming more stars. And when you get to high redshift, the quiescent population that you normally see below the main sequence is very rare. and there's only an occasional galaxy down there that isn't being included because they're so rare that the contour level isn't picking up here. So how does this change with local environment? Well, to give a clear picture on what any environmental dependence is happening, I will separate each of these samples by local environment, just dense and field, so the most extreme environments in terms of sparse and dense environments, and separate those again by color, whether they are star-forming blue or quiescent red. And here's what we see. There's a lot to break down. So if you look at the teal and dark blue lines, the dark blue is star-forming galaxies in dense environments, and the teal line is star-forming galaxies in field environments. The orange and red line are quiescent galaxies in dense environments, and the magenta purplish line is quiescent galaxies in the field. What you see is that across cosmic time, quiescent galaxies, whether they be in the field or in dense environments, are basically consistent with each other. You don't see any dependence on local environment. And for star-forming galaxies, they're fairly consistent with each other up until a redshift of 1, in which you see the star-forming galaxies, the massive star-forming galaxies, in dense environments host lower star formation rates than their peers in the field. And so we believe that the evolution of the main sequence is purely being driven, mostly being driven due to the growth in terms of the population of the quiescent galaxies and the difference in star-forming behavior of star-forming galaxies in dense versus field environments. So to wrap up that final project, we now understand how local environment is affecting the slope of the main sequence trend out to higher redshifts than have been done before. And we also do not see evidence for dependence with environment at redshifts greater than 1. And so this is a new result that we're putting forward to the field. The downturn of the main sequence trend is being driven primarily due to the difference in star-forming behavior of the star-forming population, and also the increase in number of the quiescent population. Going into the future, we'll be investigating the distribution of infrared and X-ray active galactic nuclei to see how their supermassive black holes may be changing in behavior in time with the change in star formation rate behavior. So overall, my 4 projects looked at the change in star formation rate characteristics of the most massive galaxies in the universe and their progenitors out to a redshift 3, so covering more than 3/4 the age of the universe. We provided a new analysis of the merging BCG system, SDSS J1336, in our first paper. We examined the environmental dependence on brightest cluster galaxy progenitors out to a higher redshift than environmental studies have commonly gone before. And we have also identified new trends in the star formation rate main sequence to really give context as to how these BCGs and the progenitors are leading the way in the shutdown of star formation for very massive galaxies early in the history of the universe. Future studies are going to look more on the role of galaxy mergers and also with how these massive galaxies may show some sort of dependence with a large-scale structure surrounding them. Thank you very much for listening.
All right, we can take some questions.
Do I need to use a whiteboard marker?
I will spare you. Slide 38, please. Thank you. So something curious seems to happen in the second and third panels of the top row, where there's a difference between star-forming dense and star-forming field, and then it disappears again. Is that a physical effect, or is that statistics? And if it is real, what's causing it?
So you're talking about this one?
The fact that at high redshifts, the teal and the blue are together, and then at redshift 0.9, 0.6, it starts to separate teal.
So the behavior of the teal and blue lines is believed to be real at its high redshift end. because we do have on order of hundreds or thousands of galaxies within these samples of that high redshift. However, once you get to low redshift, you'll notice that this difference is no longer discernible. That is due to number statistics, where we lose star-forming galaxies that are that massive that are in both the field and dense environments. And so they're very rare, and we really can't confidently say what's happening in these specific bits.
Thank you. Other questions? Victoria?
Are there any other facilities or, for lack of a better word, wavelengths that you can look at that would help improve your high redshift view of the environments that these galaxies are in?
So for high redshift environments, one of the limits is how the maps are measured. So how the maps are measured is that you take a certain slice in redshift, and then you measure the total number of galaxies within a given radius of a given point on the map. But then each one is weighed by the fraction of their redshift estimate within that slice. And so as you add in more and more galaxies that have spectroscopic redshifts and that are definitely at a given distance, that will improve maps with time. And so that's something that'll just take a really long time, and as the big wide field spectroscopic surveys get started. And so that's really what I'm looking forward to as the next big improvement for environment estimation.
I have a question from Andrew Lipnicki. For project 3, do you think that the lack of a strong change in Cercic profile is due to a real effect or due to low numbers in your sample?
So hello, Andy. So his question was, is this lack of evolution in Cercic index real or not? Does it depend on your number statistics? And yes, I think it depends on number statistics. It gets very tough to measure the light profile once you get out to high redshift, and basically everything's kind of a smudge. And so it makes sense that things kind of converge to a given value that you can't really, make a distinction between these different values. That's again something that would be really cool to know, but we're very much limited by the quality of the data that we have, because it's only down to a certain depth, and with that observation depth, you can only see surface brightness features of a given brightness, and that really limits you in how well you can make estimates like this.
Other questions? Joel?
So if you go up to slide 36 or 37, this is right before the one that Michael was asking about. Yeah. So if you go to the next one, I'm sorry, Kevin. I was trying to superimpose the completeness dashed line mentally on these. Is completeness affecting any of your conclusions here, or maybe I missed the point of what you were saying about this specific plot?
So for these conclusions, what I've done is I've plotted the completeness limit as the vertical dashed line. I should have said that earlier. And so that's telling you that everything above that line, we have over 90% of the galaxies detected, and it's well defined. One plot that I didn't have time to talk about today was how we measured the slope of the main sequence. And at low redshift, there's work in the literature that really separates the slope of the main sequence for galaxies that are above 10 to the 10 solar masses and galaxies that are below. What mass completeness does is limits our ability to measure that low mass slope at high redshift, because you're only observing a fraction of the galaxies, and it's just not a confident measurement at all. And so that was the point.
Okay. Thanks.
Can you go back to the slide that had the illustrious deposition rates and then the observed mass change?
Oh, yeah.
Sorry. My question, I've got two related, is there a reason why the illustrious rate is secularly higher consistently? So, in the line beneath it.
So, as of right now, that line is 100% efficiency of stellar mass being delivered onto galaxies. And so if you lose any sort of efficiency with that, then you're going to have that line naturally decrease and meet the stellar mass growth line itself. Then the stellar mass growth line is motivated by the stellar mass selection cut that we had defined as the change in number density. So since this green line is coming from how fast galaxies need to be growing to account for that number density evolution, they are slightly different quantities that, like, it needs a lot of discussion to go into like how those numbers are coming to be.
My follow-up to that is there's now the illustrious TNG results, which have
Yes.
self-measured description. Have you considered how that changes that?
I have considered it, but illustrious TNG is also a much smaller volume because they added in all those other details. And so with a smaller volume, you're becoming less confident in the most massive ends of the galaxy stellar mass function, since you're no longer getting a high number of these really exceptional objects.
Do we have any other questions from the laptop?
One for me though.
From you?
Yeah.
Go ahead.
The previous slide. So, can you remind me what you said the number change was between whether you did correct for AGN or not?
Oh, so the number change in terms of how we identified galaxies? Or-
No, the star formation. Was it?
Oh, yeah. So for this specific example, it is the same galaxy, just with an AGN component or without. The top inaccurate fit has a star formation rate of about 256 solar masses per year. And the one on the bottom, which includes an AGN being responsible for some of that emission, means you only have a galaxy that is forming stars at 46, 45 solar masses per year.
So my question is, this difference in star formation rate, that can drastically change where it lands on that star formation rate, stellar mass sequence, right?
Yes.
So I'm curious, because I know SCD3 fit takes a lot more time to run. If someone were to not correct for these AGN, how, if any, like what effect, if any, would there be on the current idea of galaxy life from progenitor to quiescent? This change, like, would that affect these types of studies?
So definitely would affect these types of studies. Well, AGN can be rare. Their frequency increases as you look earlier in the history of the universe. And so if you don't correct for them and include good estimates for their stellar properties, what you're going to do is include fits that have overestimated star formation rates as your fitting routine struggles to account for all of that emission purely due to stellar processes. Additionally, it will bias your stellar mass estimates higher. And so that means that your points will usually be offset here. If you include galaxies in the AGN but don't fit the AGN, they'll have overestimated star formation rates. Crystal's currently working on a paper showing how that changes with time. So advertisement for that coming up, Tyler and all 2019.
2019. All right.
We have time for one more question. Michael.
If you go to slide 37, the one Joel commented on, I see all kinds of interesting outlines in those beautiful blue shapes. Do you have a favorite outline? Is it a bunny or a
This guy.
It's all abstract to me.
There might be butterflies in there.
That was the ambush question for the day.
Right, anything else? Okay, let's thank Kevin again. Right, at this point, we will have the closed committee session. Before you go, those of you in school officials will be, including the graduate students, just a reminder that there is a graduate recognition this afternoon at 5 p.m. in the Carlson Auditorium.